I'm going to tell you about deep generative models, and this is one of the research areas that I've been really excited about in the last few years. Before I start, I want to mention that Ian Goodfellow, Aaron Corvell, and I wrote this book called Deep Learning, which is available from MIT Press or at Amazon, but you can also download 3 chapters online. And the last part of that book is the third part is really about deep generative models, so you can learn more there. So before I tell you about generative models, let me tell you about intelligence and AI. For a long time, researchers have understood that in order to make computers intelligent, they need to have knowledge. And the question is, where did they get that knowledge from? What really has worked in the last few years is to provide that knowledge through in the form of learning from examples. Previously, researchers are trying to give knowledge directly. This was classical AI, where we tell computers about facts and rules. But unfortunately, a lot of the things we know are not communicable. They are intuitive. So we can't tell the computers some of the things we know. They're things we know when we recognize them, but we can't explain. So we need machine learning. Now, the progress we've made in the last few years is pretty amazing, but it's mostly based on supervised learning, where the humans tell computers how to interpret, for example, images or sounds or text. We believe that there are some limitations to the kinds of learning we're doing now that humans are able to deal with. One way to see some of these limitations is to consider ways in which the current systems make mistakes. They tend to not generalize that well outside of the training context, and they can be fooled. For example, in the image, you see the image of a dog, but by changing the pixels ever so slightly, we can make the classifier of the neural net say that it's an ostrich. So I believe that we still have a long way to go to allow computers to discover autonomously the high-level abstractions that explain the world around us. And unsupervised learning is crucial for this. So humans can learn all kinds of things without being taught. A very good example of this is intuitive physics. Parents don't tell their kids about gravity and Newton's laws. Instead, they figure it out by just observing the world and interacting with it. So babies somehow just build this internal model of physics. It's not based on equations, but somehow it's in their brain, and it's learned through examples. Can we do something like this? Well, before we get into this, I need to tell you something a bit more general about deep learning and about representation learning, the notion of distributed representation. The idea is that inputs like images, text, sounds, whatever, can be represented, can be transformed from the original representation, like pixels, into representations that are more appropriate, more abstract, that allow the computer to do things that are useful. And this is the objective of deep learning, really, to allow computers to learn good representations. And we call them distributed because the information is distributed across many quantities, like the artificial neurons activations. And there's something really important theoretically about these representations that we start to understand theoretically in the last few years, which is that they allow us to deal with what's called the curse of dimensionality. So when the computer is trying to learn from large, high-dimensional inputs, the number of configurations of variables can be exponentially large. And in theory, it could be even impossible to learn unless there's some kind of structure in the data. And precisely that's what deep learning exploits. It exploits a form of compositionality, that the world can be explained by composing pieces, by different units expressing different aspects of the world. That's the idea of distributed representation. And with depth, by having different features computed in terms of simpler ones at different levels of representation. So in fact, when you train deep neural nets for different kinds of object recognition, you find that hidden units represent different aspects of the world that they may not have been thought about before. So here we see what different neurons in this deep convolutional net prefer in terms of input. So there is like a unit that likes tables, and another one that likes lighting fixtures, and another one likes animals, even though this particular network was never trained to recognize these particular categories or these particular concepts. But it discovers sort of a representation of the data which has actually a semantic meaning, and where, say, each image is represented by a bunch of features, like in the case of the example and the slide. Does the person wear glasses or not? Is the person a male or female? Is the person a child or not? You can think of these as a large set of binary features, actually they could be continuous, which characterizes any particular input here, a particular image of a person. And so because each of these features can be, say, on or off, or more or less active, that captures an exponentially large number of potential variations in the data. And also, these kinds of representation can easily allow us to predict high-level semantic things we care about. So the big question is, unless we hard code the meaning of these representations, which is not what we want to do, we'd like the computer to discover that. Well, how do we do that? How can computers learn from data to discover in an unsupervised way, in an autonomous ways, these kinds of representations? So one interesting concept that helps us understand what we're looking for here is the concept of invariance and disentangling. It's a very old idea, the idea of invariance in object recognition and computer vision and speech recognition. If you're trying to recognize object categories, then you'd like your features by which you're going to represent the image to be invariant to the position of the object in the image. Similarly, if you're doing speech recognition, you'd like to extract features or representations that don't change when we change the speaker, but only change when we change the content of what's being said. So this is a form of invariance. But when we do unsupervised learning, we don't know ahead of time if the sound that the machine is hearing should be categorized eventually in terms of what is being said or who's saying it. So we don't actually want to throw away information. We just want to reorganize information so as to separate or disentangle the underlying factors that explain the data. And we believe that if we can do a good job of disentangling, then again, we essentially beat the curse of dimensionality, and we're able to solve all kinds of problems with very few examples from this point on, once we've learned these representations, which is one thing that humans are good at. Another important idea regarding learning of representations is that we really want to learn multiple levels of representation, which correspond to multiple levels of abstraction. In fact, this thing that I just said is exactly the heart of what we meant when we decided to call this deep learning. And we believe that there's going to be a huge payoff by being able to learn higher level abstractions. I believe that right now we are learning fairly good representations, but low level. We're not yet able to learn higher level abstractions that really disentangle the underlying factors of variation. Okay, so now I'm going to get a bit more technical and start telling you about particular families of approaches to learn representations. And one of the most important idea in this respect is the idea of autoencoder. So it's very simple. I'm assuming that most of you already know the basics of a neural net. So we're learning a transformation from an input to an output, and usually the output would be some kind of classification that we're trying to make. But here we're going to do something different. Imagine we have a neural net that goes from inputs to a reconstruction of the input. So in other words, we're just going to map the input to itself, which sounds useless. But we're going to do it in two steps. In the first step, we're going to encode the input into a new representation. And in the second step, we're going to decode from that representation back to the input space. So really what we're learning is a two-way mapping from the raw input space to some intermediate representation. And of course, we could do this hierarchically, so we can then map this new representation to an even higher level representation. But the point is, really what we're doing here is just transforming the space mapping the input to a new space in such a way that we do preserve the most important information in the data. And one of the measures that's often comes up in these autoencoders that we care about is what we call reconstruction error. In other words, can we actually go back? Can we go encode and decode and recover the original input? And the difference between the reconstruction and the input is called reconstruction error. So we can measure that error, and that's often part of the training objectives for autoencoders. Now, there's a lot of variety of autoencoders, and sometimes the mapping from input to representation is just deterministic, so it's just applying some computations, fixed computations. And sometimes it is stochastic, so that's why on the slide you could see some symbols here representing conditional probability distribution. So you could say the code is somewhat random. Maybe there are multiple interpretations for the same image, and we are going to allow the representation to capture all of these interpretations. Similarly, given a particular representation, maybe there are different ways of expressing it as a low-level representation. So the mapping from code H to pixels X could also be probabilistic. Another important concept is the concept of latent space or latent variables. So as I said, the relationship between the raw image or raw input and the representation space could be stochastic, in which case we think of the that latent space, that space as a latent variable in terms of probabilistic models. There's also the idea that we can use the encoder and the decoder to generate new configurations and new images, and I'll come back to that. For example, we could generate we can have a distribution over the hidden representations, the latent representations, the codes, and then from there apply the decoder in order to produce, say, the images. Another idea that you see in this slide is that one thing we'd like the encoder to do is to transform the input distribution into a simpler one. So in the figure, what we see is that the set of images is like a spaghetti here. In other words, if we're able to show all of the possible images in 2D, it might only occupy a very small part of the total 2D space, which is this red curve. So this is what we call a lower dimensional manifold. And so, each point here would be an image, but the only legal images would be the ones on this manifold, and other things don't look like real, actual, natural images. In fact, you can verify for yourself that something like this must be true, because if you pick pixels in an image randomly, independently, you get just a white noise image. It doesn't look at all like a natural image. So that must be saying that the set of images occupies a very small volume in the total set of all possible images. Okay, so that's very special, but it's true for many natural data that the kinds of configurations in the space of the data, the raw pixels, for example, is occupying a very tiny volume in the total. So we typically have this mental picture of manifolds. Okay, but what makes things more complicated that those manifolds are not like nice, straight, flat. Instead, they are curved, and really think of them as like a big spaghetti in like maybe some sheet that's turning around. And that makes it very difficult for machine learning to figure out, predict things from that kind of data. So what the encoder should be doing really is taking this spaghetti and somehow nonlinearly transforming the space so that the spaghetti becomes flat. And if the spaghetti is flat, it becomes very, very easy to do things and to, for example, interpolate between points or to predict one thing given another thing, because everything becomes linear. There's another related concept that has to do with these two-way maps. We can have maps between inputs and representations, but we can have different kinds of inputs. For example, you can have images on one hand, and you can have sounds on the other hand, or you can have texts. And now you can imagine some kinds of transformations between those different modalities, between, say, images and text. In fact, people have trained models that go from text to images, or from images to text, and so on, or from one language to another language. So we have all of these different types of data, and we often care about learning transformations from one type to another type. Now, a convenient way of learning these kinds of transformations is to use autoencoders to do the transformation not in the raw space, but in the more abstract space. So if I'm going to map a sentence in French to a sentence in English, I'm much better off first mapping the French sequence of characters to some kind of semantic representation which really captures the meaning, and then map that to an equivalent representation of meaning in English. And maybe in that case, it's the identity transformation, because French and English basically express the same things. And then use a decoder for the other modality to go, like English, to go from the high-level representation back to the raw space here, say character sequences in English. So we have these relationships shown in the picture, right? So we have sort of the direct relationship between the low-level things like the X's and the Y's, but that's hard to learn. Instead, we can have autoencoders that go from the low-level representations in the X space, like French or images, to a high-level semantic space, and these could be two-way maps with encoders and decoders. And we can do that for both modalities. And then we can also have transformations that go from the representation of corresponding to one modality to the representation corresponding to the other modality. And that's much easier to learn because we're talking about these more abstract levels of representation. So this is actually how we do transformations between text and images, either one direction or the other direction. And one nice thing about this is that it enables what's called zero-shot generalization. So it may actually allow us to generalize to, say, words that we have actually never seen being paired with an image. Maybe we have never seen the word puppy paired with the image of a small dog, but maybe we've seen puppy with other text that really helps us understand that this is a baby dog. And we have seen other images of baby animals. So by bringing things at the right level of representation, which is semantic, where we talk about dogs and we talk about baby things, we can actually learn the mapping and generalize to words or concepts that we actually never seen paired in both modalities. Okay, so now let me jump into the actual subject of generative models. As I said, we are trying to do unsupervised learning, so we don't want to tell the computer what the underlying concepts are that explain the data. And there exists a vast array of possible ways of doing unsupervised learning, or rather even to frame the problem of unsupervised learning. And in fact, it's still kind of an open question, what is the right way of doing it? Maybe there is multiple ways and that's it. And one way to see that a computer actually understands the data, the distribution behind the data, the structure behind that distribution, is to ask the computer to generate new examples that should be coming from the same distribution. So maybe the computer has seen hundreds of thousands of images of faces, and now we'd like it to invent new images of faces. So what we can do is we can train a model like this red box, which takes in random numbers, and of course it has parameters, and it outputs generated samples. And if we put in different numbers, different random numbers, we get different generated samples. But notice here that it's very hard to do that, because remember I said that natural images are very, very special. If I take like random pixels, it doesn't look like images, and it doesn't even less look like faces. So to take in random numbers and generate just images of faces is actually very difficult. So what we are seeing here are some of the current state-of-the-art samples generated by one of the GAN models called BGAN. That's pretty amazing. You can see some things that are not quite right, but it's much, much, much better than what we were able to do a few years ago. Let me tell you a few more words of examples of different types of generative models, but later I will focus a bit more on the GANs. So actually, a very old type of generative model that is related to the GAN is called the Helmholtz machine, and that dates back to the mid-90s. A current sort of descendant of this is the variational autoencoder, for which there's a rich recent literature, where this started around 2014. The idea of these Helmholtz machines and variational autoencoders is that we're going to have, again, an encoder and a decoder, but they're going to be of the probabilistic type that I mentioned earlier, so that there's going to be a probabilistic transformation from inputs to representations, and from representations back to inputs. And there's also going to be, if you see my cursor, there's going to be on top here, the CP of H3. So that's a sort of prior probability of generating things in the high-level representation. So if we actually want to generate images, we would sample from the distribution in the high-level space, and then we would go down in this generative neural net each time, potentially adding some random details. That's what each of these conditional distributions really mean. And eventually we generate the pixels. But so you see that when you generate, you only need these arrows that go from the high-level representations through the different steps of the decoder into the pixels. But the way we're going to be training this model involves also an encoder, which goes from inputs to high-level representations. And some of the GANs also have encoders, although the original GAN only has a decoder. Right. Oh, one thing to say about this is that the training objective for these kinds of models is actually an approximation, or a lower bound more precisely, on the log likelihood. Log likelihood of the data is sort of the most common way in machine learning and statistics that we try to fit models to data, and says that we're trying to find the parameters of the data that maximize the probability that our model could generate the examples we have, the training examples. But it's not the only principles, as you'll see. So these Helmholtz machines and variational autoencoders, just one out of a large number of types of generative models. Some of the earliest ones that have been popular in the machine learning community are the Boltzmann machines, or restricted Boltzmann machines, which is a special types of Boltzmann machines, which we call RBMs. In fact, the beginnings of deep learning around 2006 were due to progress in training deep neural nets by stacking RBMs. So each of these restricted Boltzmann machines were used to train one level of a deep neural net. So that's how these started. The original Boltzmann machines actually started in the early 80s, so it has very long history, which date back to the beginning of connectionist approach to neural nets, not so far from those we know today, actually. Later in the 90s, we had those Helmholtz machines, like sigmoidal belief networks, which I explained a little bit. And well, at about the same time as we played with RBMs, we found that we could train deep neural nets by composing straight autoencoders, and then quickly after we found that we could do slightly better than the simple autoencoders, which just minimize reconstruction error, by introducing a notion of denoising. So instead of the autoencoder just trying to reconstruct the original input, we give it a slightly harder task, because we don't want it to just learn to map the input to itself. That's too easy. That would be just the identity function. So we ask the autoencoder to actually correct the input, to remove the noise in it. So what we do is we take an image and we corrupt it by adding noise, but then we ask the neural net to reconstruct the clean version, the original uncorrupted image. And that actually forces the autoencoder to learn about the distribution, and we've recently understood how that captured the distribution, and also how you could use this for generative models. That's actually very close to the variational autoencoders, which I mentioned, and which are currently studied a lot and used in a bunch of models. Another family of generative models that I won't have much time to talk about, but is really very important, is the family of autoregressive neural networks. And if you've heard about recurrent neural networks, well, they actually are also generative models, which, like all of the models in this family, they all generate the image or whatever you want to generate one item at a time. And they do it by generating the next item by sampling from a conditional distribution, the next item, given all the previous items. And the recurrent part allows the model to remember the things that have already been generated, the items like the pixels that have already been generated, and from those pixels, figure out what are good values for the next pixels or the next pixel or the next piece of the data that we want to generate. And finally, maybe the most recent family, but really studied a lot in the last year, is the family of generative adversarial networks. And I'll tell you more about that. But there are really a lot of others, and it's a very rich domain of research. Again, if you want to learn more, see the last part, the third part of our book on deep learning. So let me say now a few words in the last few minutes on GANs, for generative adversarial networks. The idea is that we're going to learn an objective function, a training objective for a generator. So remember, I told you that we could have a neural net or a black box that takes random numbers in and outputs generated images. The question is, how do we train it? How do we train it to generate things that look like the training data? Well, the idea of GAN is very simple. We're going to train another network, which we call the discriminator, that's going to try to figure out whether the images generated by the GAN generator are real or not. And so that discriminator is trained to say whether the input comes from the generator or comes from the training data. So it's a normal binary classifier. And once it's trained, however, it could provide a signal for training the generator, because we would like the generator to change its parameters so as to fool the discriminator. So if the output of the discriminator says, with some probability, this looks like a real image, would like the generator to change its parameters to increase that probability. So to produce an image that's slightly better in the sense of making the discriminator think that it looks more like a real image. So when we use the model, we just use a generator. So we have the generator. But when we train it, we're going to couple the generator with a discriminator, and we're going to use the gradient of the generator, the discriminator's output with respect to the generator's output to train the generator. Okay, so when we started working with GANs, it didn't work that great. You can see some of the MNIST digits were pretty good, but images of faces or natural images like CFAR were not that great. But the good news is that about a year later, other researchers started exploring different ways of training the GANs and starting to have quite impressive success. So this uses a particular type of architecture for convolutional nets that are used in the generator and the discriminator, and was trained to generate images of bedrooms. And you can see it's much, much better than our original work on GANs. And the nice thing with GANs, as well as many generative networks which have a latent space, an internal representation, is that we can actually play with the representation and interpolate between representations or add, subtract different representations. And for example, we can take the representation corresponding to one image and the representation corresponding to another image, and we can show all the intermediate images corresponding to interpolating in the high-level space. Of course, if we were to interpolate in the pixel space, it would be very ugly. It would be just like two images superposed. It wouldn't look like a natural image. But the good news is that when we interpolate in this representation space, and then we map back using the generator or the decoder to pixel space, we see images that look natural. And so we can go from an image, for example, that has a window at one place to an image that has a window at another place, or we can go from an image that has a fixture on ceiling to one that doesn't. And it seems to somehow find a way to do a transition between these kinds of images. And you can do things like take an image of a man with glasses and subtract the image of a man without glasses, and then add the image of a woman without glasses and get images of women with glasses. So you can play all kinds of interesting games, and that has been done a lot recently. There are all kinds of issues though with training GANs, and one of them is that it's difficult to train them to work on a large number of categories. But you can also train them sort of jointly when you tell the network about the categories, in which case you can actually train. You see these are generated images of volcanoes, but this one actually was trained on the full 1,000 images of the ImageNet data set. So 1,000 categories, and you can see that it does pretty well on a bunch of categories. So that's one approach. But there are still quite a few issues with training GANs, and there's a lot of research going on. So the first thing that we observed is that training a GAN can be unstable and diverge. So sometimes the training goes well for some time, and you can see that the images being generated are nicer and nicer, and then suddenly things get bad, and you can see some of the training objectives going in strange ways, and basically, the network is gone in a bad place. So what is going on? And there's still, I think this is still an open question, but one thing for sure is that GANs are very different from traditional machine learning, in the sense that traditional machine learning has one clear objective function, and so we optimize the parameters with respect to that objective function. We're trying to minimize some kind of classification error or reconstruction error or some likelihood, and we can measure that objective during training, and we can see that it gets better and better, and so that's sort of convenient and practical. But here we have these two networks, right? So if I go back, we have these two networks, the generator and the discriminator, and each of them is actually optimizing a different thing. So in fact, this is called adversarial because, in fact, not only they're optimizing different things, they're optimizing things that are adversarial. So, the things that make one perform well make the other one get worse, because the generator is trying to fool the discriminator. So we're not at all in the traditional machine learning framework of having one objective function to be optimized. Instead, we are in a kind of game theoretical world where we have these two agents, each of which is trying to optimize its own objective function, and so that's much harder to understand mathematically, and much harder to monitor. How well are we doing globally? So unfortunately, right now, the way that we are mostly monitoring the performance of GANs is that we're just looking at what's generated. There are other in principle, there are other things we could do, and various things have been proposed, like trying to actually convert the generated distribution into some likelihood, but I'm not yet convinced that this is always reliable. And in principle, also, if you were to train the discriminator well enough for each configuration of the generator parameters, you could also, under some conditions, you could also, like if you regularize the discriminator, you could also use the discriminator loss as an objective function that tells us how good the generator is. In other words, one way to think about it is that as the generator gets better, it should be harder and harder for the discriminator to do a good job, right? I mean, as the fake images look more and more like real images, then the discriminator ability to discriminate between the two should get worse, and so that that's what we'd like to see. However, in practice, it's not that simple because we don't typically have the time to train fully a discriminator for each particular training step of the generator. Go back here. So one of the things that has been observed from the beginning is that the training of GANs can be very, very sensitive to hyperparameters and the particular details of training it. So the main thing is that if you start playing with GANs and it doesn't seem to work, well, don't get discouraged too quickly because others have gone through the same issues. And there's now a large literature of papers precisely trying to address this. And so, it's worth reading those papers and maybe trying some of these ideas. For example, things like adding noise or training in some form of mini batches can be pretty useful. So let me say a few words quickly about some of the other ways in which training can fail. So one thing that happens sometimes is what's called mode collapse, where the training diverges in a particular way that makes the same image, which usually doesn't look like a real image actually, come up many times. So it's like the network gets obsessed with a particular type of image and it always generates the same image or something very close. And a variant on this is what's called missing mode. So maybe what it generates actually looks nice and there's some diversity, but there's not enough diversity. But there are types, subtypes of the data that are simply absent. So if you're training on the 10 MNIST digit categories and it only learns to generate 6 of them, then 4 of them are somehow forgotten by the model. And it turns out that if you analyze mathematically the training objective of the GAN, it's fairly easy. There's not a big price to pay for the model to forget about some of the types of data, some of the subcategories that are in the data. So this is, again, something that people are studying both experimentally and theoretically. But that's important to know, that having good diversity in the generation is important. In fact, one extreme version of this is that if your GAN overfits, it could just learn the training examples and not produce any new things. Although typically that doesn't happen because it's fairly hard to train GANs. But one way to verify that it's not just copying training examples is to take the images that are being generated and compare each generated image with each of the training examples. And if they match, if they're very close, then we know that it's sort of cheating and just copying training examples. Because of course, you could have a generator that just copies some of the training data and it would look very, very nice, right? But that wouldn't be very interesting. It wouldn't mean that the model has learned something about the data distribution because it doesn't generalize to new configurations. As I mentioned, one of the challenges is to train models with a diverse set of underlying types like categories. So one way to cheat is to say, oh, we're only going to train on one kind, or we're going to tell the machine what those categories are during training. So like we do in supervised training, we both provide the images and their categories. We can do that with different models. One hurdle, I already mentioned that it's difficult to monitor progress, but more generally, we don't have an accepted quantitative measure of quality, although again, there are proposals. So why, with all these difficulties, are people continuing to explore the GANs? Well, one thing is that sometimes you can get these amazingly nice images and actually applications that they built around them. And also, it's so different from what has been done before in machine learning that there's the hope that it could bring us even better things in the future. So if you want to learn more, I suggest you look at, in particular, Ian Goodfellow's NIPS tutorial at the last NIPS, and of course, a rich literature on the subject. All right, so I'm done, and I would like to thank the many people in my group here at the Mila in Montreal. I supervise around 25 students, and I work with 5-6 other professors, and we're now about 110 researchers in Montreal doing deep learning. Well, thank you for your attention.